Good morning, good afternoon, and good evening, everyone. So today we're going to be doing double integrals again. We're going to do more exercises on double integrals, but this time we're going to be doing a double integral, not over a rectangle, but we're going to do it on more general regions, right? Because you can't do it forever on rectangles. What if we had more general regions, right? And so I'm actually going to do something a little bit different with my studying here. Instead of me talking about the textbook, I'm going to go ahead and jump into some exercises because I think that's easier. Let's try doing that. Okay, so for number one, we're being asked to evaluate the iterated integral. So basically, it's just a double integral, right? So let's quickly do that. So our iterated integral is as follows. 0 to 0 square root of y, 5xy squared, dx dy. And so these are the same steps actually. So let's go ahead and evaluate. Starting from dx here. And so what is this going to be? Well, my y is a constant, my x is the thing that we're integrating. So we're going to do 5y squared of my integral of x dx. Then we're going to integrate. So we're going to be, let's say this is x squared over 2, right? Let me do that. 0 square root y, okay? And then what else can we do? We can kind of take out this 2. So I'm going to do 5y squared over 2 of x squared, right? And then this is just going to be what? Am I doing this correctly? I'm integrating in terms of x, but then it's showing me a y. So I plug in the y here. Yeah. Because again, we say that y is a number. So let's just plug it in. So we have here square root y squared. So we have y. And so we have 5y cubed over 2. And then this one's just 0. So that's basically nothing. And then that's that. Now we do our outer integral, which goes from 0 to 2. And then here we do it with dy. So the nice thing we can do is eliminate constants. So 5 halves goes outside, y cubed dy. And that's an easy integral, right? This one's just 5 over 2, y fourth of this. We could multiply the 4 out, so this is going to be 5/8. So again, I'm trying to keep it as nice as possible. Y to the fourth squared. What? Why did I say squared? 0 to 2. And then I have 5/8 times 2 to the fourth power. Oh, my bad. I messed up getting my calculator. So that's 2 to the power of 4. That's 16, right? And I can cancel these. 1, 2. So here I get that. And then that's my answer. Let's try, see if we get. Let us see. What's the exact value of this thing? So it is a 10. Okay, I'm just trying to double check, see if I'm doing my computations correctly. But overall, it's the same idea, right? Okay, number 2, same thing. We want to, again, evaluate our integral. So it's the same idea. So that way, when I go through exams, I can immediately recognize this pattern. This is what the thing I hate about math, but it's absolutely crucial for academic math, and that is quote unquote memorizing / understanding the pattern. Okay, so here's our integral. It's 0 to 1. It's a double integral actually. 0 s. So instead of x and y, they changed it to d and s, I believe. Cosine of s to the 9. And then this was dt ds. So here I integrate with respect to t first, and then with respect to s. Okay, so the first thing I'm going to do is this dt. And let me solve that integral. What is the antiderivative of this? It's actually just 1 over... So here we think of S9 as a number. We think of that as a number. What's that going to be? 1 over S9. Then this one's going to be sine. Right? How do I know if I'm correct? I check the derivative. So if I take the derivative of this, say this was 2, let's say. So if we take the derivative of... Oh, shoot. Wait a minute. This is s to the 9th. So, here's how we're going to do it. We take the derivative of s to the 9. Okay, why did I write it like that? This is going to be cosine s to the 9 times chain rule of this. So in this case, this is just 0 because it's a number. This thing's a number. Oh, okay. So if this was a number, I want to include a t in it. So it's actually just a number. So there's the confusion. It's a number times t, right? That's what makes it confusing. Okay, and then from here, we just plug it in to t. So we plug it into t, we get S8 cosine s to the 9th. And that's it. Let me actually put this to the other side here because it's easier. And then from there, so I put a little check mark. And then I now integrate with respect to s. So 0 to 1. So here, this is S8 cosine s to the 9th ds. Now, the thing that makes this... Oh, why I put 9? It's supposed to be 1. Okay, let me double check if I'm... Yeah, so it's 1. That was 9. What the hell? Okay, so this is 9. This is 1. This is 1. And then what is this? How do I integrate this thing? So here we treat s as a variable. I have two things here, so might as well. Let me think. Well, if I do a use of... Let's try doing a use of... If I pick u to be s of 9, my derivative would be 9s8. So I think that makes sense, right? And so my 9s8 ds. And so my ds is 1 over 9s to the 8th du. And then when my s is 0, my u is 0 to the 9th, so that's 0. And then when my s is 1, my u is also 1. 1 to the 9th is 1. So I have this integral of 0 to 1, s to the 8th, cosine of u, 1 over 9s to the 8th du. And this gets canceled. And so I get 1 over 9, 0 to 1, cosine of u du. Right? So very, very tricky integral. Yeah, so u sub worked. And then this is when I integrate. So I get 1/9 sine of u, 0 to 1. Then I get sine of 1, which is something. Sine of 0 is 0. So I basically get sine of 1 over 9. That's the answer. That I think should be correct, question mark. But we'll see. Again, I'm not super sure, so let's have a check. Oops. Okay, let me actually just write this. Integral, or double integral from 0 to 1, then 0 to s to the 8th. Then the integrand is cosine of s to the 9th. And then the dt ds. So integrated with respect to t first. And then from there, I integrated with respect to s. And so I get, yes, I get sine of 1 over 9. Okay, let me just type it out, see if I get. If I submit, see what happens. And there we go. Nice. Okay. Now I look at number 3. So number 3 is telling me to do this. Evaluate the double integral. And so this double integral is telling me the 6y over. So this is the double integral, 5x to the 5th plus 1 dA, or that change in area. And my domain, oh shoot, why do I call it domain? My D, or that general region, is the rule such that if I have these, I forgot I wasn't going to write it that way, but here I think I should. Yeah, I should write it that way. So x is in between 0 and 1, y is in between 0 and x squared. So now this is a more general region that we're looking at. So here, what I basically do is find integral and solve it. That's all I have to do. So what's the integral? First, let's try doing 0 to 1 for my x. For my y, it's 0x squared. Put my function in. What's this? dy, and then dx, right? And then I solve it. So here I have 0x squared of this thing, 5x to the 5th plus 1 dy. Now, how do I solve this thing? This is a number. 5x to the 5th plus 1 is a number. 6 is a number. So I basically get 6, 5x to the 5th plus 1, 0x squared y. Right? Because these two are numbers. And then from there I get, okay, 5x to the 5th plus 1. This one is integrated y squared over 2. I could cancel this. 1, 3. Right? I could do that. And then from there I get x squared, so x to the 4th. So I get 3x to the 4th over 5x to the 5th plus 1. I can't do it by a 0, because then that would be just minus 0. And that's it, right? Now I integrate this with respect to x. 0, 1 with respect to x. Right? Dx. What can I do? Okay, I can take out my 3. Use one of my integration techniques. What do I know? Let me think. I could, What if I do u as x to the fifth? What if I do that? Let's try. There's no harm in trying. What if I do that? Then my du is, or my derivative is 5x to the fourth, right? That doesn't seem nice. This is dx. Actually, this looks promising. It looks no, this looks promising, I would say. And then this is dx. Then I have dx as 1 over 5 5x to the fourth du. Right. And then when my x is 0, my u is 0. When my x is 1, u is also 1. So I actually have a new integral here. This is 3, 0 to the 1. So this one is x to the fourth over 5u plus 1. Instead of dx, I get 1 over 5x to the fourth du. And here I can cancel this one out nicely. Then I get 3 over 5. So this is just me peeling everything out. All that. I get 5u plus 1 du. I could do another u sub. Sure, let me do another one. Let's say v is 5u plus 1 dv. So I take the derivative of this thing, I get 5, right? I think I get 5, right? Uh-huh. I get 5 du. Du here gives me 1 over 5 dv. And then when my, this is where it becomes different. So when my u is just, actually, do I need to? Or could I just straight up integrate this whole thing? I think I could just straight up integrate. I don't need to. Too much u sub. I'm just gonna straight up integrate this thing. So here I'm gonna get 3 over 5 integrate ln of 5u plus 1. This is 0 to 1. This gives me 6 ln 6 minus ln 1. ln 1 is 0, right? So I don't need to include it. So I basically get 3 ln 6 divided by 5. And then that's my answer. I could have done another direct substitution, but I don't think I need to. It's one of these cases where I don't think I need to. Okay. Let me see if I get that one. 3 ln 6, which I divide by 5. Also, let me double check. Let's see if you actually got this one. Let's see. Yes. Oh, wait a minute. Whoops. There's a 25 somewhere. I'm missing something. Did I miss something? I think I missed something. 3. 3 to the fifth. 3 L. Right. I missed the 25 somewhere. I don't know where I missed it. 0 to 1. Did I get that part? At least that part. Okay, I got there. Oh, so I did a different. Yeah. It made me do. There is a different use of here. Yeah, there was a different use of here. Wait, let me see. This doesn't make any sense. There's no way. Oh, now I know where I messed it up. There. I have an extra 5 here, and then I have this. And then I did an ln, which again shouldn't be Yeah, so let me just do another u sub. Let's just do another u sub, just to be super, super, super sure. So v would be this. So in this case, it's a v sub. It's basically a direct substitution. So my derivative would be 5 du. And so my du would be 1/5 dv. And when my v is 0, my u is basically 1, right? And when my v is 1, or wait, what am I doing? When my u is, I have it in reverse. When my u, oops. When my u is 0, my v is basically 1. When my u is 1, my v is basically 6. So I have a new integral, 3/5, 1, 6, 1 over v, right? Then my du is 1/5 dv. So I get 3 over 25, 1, 6, 1 over v dv. And then I integrate, so I got 3/25 ln of v, 1, 6. And then there we have it. So 3 ln 6 over 25. There we go. Yeah. AI did a different way. He immediately used a u sub on the 5x fifth here. Because apparently you can, and you get immediately the 25 outside. Here I was just trying to make sure, but yeah, this was a slower process, but idea is the same. So yeah, same idea. So 3 ln 6 over 25. I don't like solving this. Okay. And I'm nice. Let's see. Number 4. So here we want to set up iterated integrals for both orders of integration. Okay, maybe I might have to refer to the textbook on this one. Iterated integrals for both orders of integration. So what in the world am I talking about? I don't know. Something I have to look at. And then we're being asked here to evaluate the double integral. So this is where I'm going to refer to the textbook. I'm not going to read the whole thing, just parts that I need using easier order. Or I could just learn computational techniques and I would be fine, right? There's a watch it here. Let me just do the watch it, see what happens. Mhm. Oh, what in the world am I looking at? I'm kidding. Let's see. So for y, type 1 and type 2. Okay. Oh, so it wants me to get both. Type 1 is when we integrate by y first then x, and then the other one is when we integrate by x first then y, right? Okay. And then we set up integrals for that. So again, it depends on the region that we're going for. Yeah, it depends on the. Okay. Mhm. Okay, so here's what we're gonna do. Just write it out first. So here we have a double integral d y dA, and this is equal to, oh, whoops, my bad. So here we're saying that d is bounded by a general region. The general region is y equals x minus 12, and then we have x equals y squared. And then from there, well, the first thing we want to do is find points of intersection, right? So here are the steps. So find point slash s, points of intersection. Where do they intersect, these two things? So we actually have a system here. So again, we could solve for this. We could say, okay, I could say this is y squared, right? And then here I have y squared minus y minus 12 equals 0, right? And then here I could factor this out. I could say this is 4 or negative 4 and plus 3, right? So here I could say this is like that. That would give me what I need, right? Now I have two solutions for y, right? So my y here is actually either 4 or negative 3. And so my x would be 4 squared, 16, or negative 3 squared, 9. Right? Those are my points. Wait, is that what the thing did? Okay, so we got that. And then let's do a type 1, right? So here, type 1, which is just dy dx. Then you also have a type 2, which is dx dy. So how do we find dy dx? Well, we need to find bounds for y, right? Do you have a function given? Oh, so the thing is, what is our function? That's another thing that we have to do, right? So here, so type 1 is some double integral of y dy dx, right? And so what's that gonna be? If our y here is equal to x minus 12 and square root of x, right? And then another thing would be y is negative square root of x. Then we also have a y that's equal to x minus 12. What does that tell us, right? Well, that tells us that, let me see. Uh, Wait, is this a line? Oh, it's a line. How do you get that? 0 and 1. Oh, okay, this one's, wait a minute. Okay, let me try. Let's try something here. Because I have to set it up. Okay, so first thing is we find the intersection points, and then we find dy dx, right? Oh, there we go. Given by, is that correct? Um, wait. Let me just double check just to be super sure if I'm doing this correctly. Mm-hmm. Oh, so we put everything in terms of x in the first thing, right? Okay, so that's what we have to do, right? So here, if we want this sort of type, then we have to have y in terms of x. So here our y is going to be plus minus square root of x. But then y is also going to be x minus 12, right? And so which one's the bigger or the upper boundary here? Oh, we just try plugging in functions, to be honest. Yeah. So let's say if we were to get something bigger than 12, like, I don't know, like 25? This gives me a 5, this gives me a negative. So this one's obviously greater than this, right? So this one is greater than this. Although there are occurrences when it isn't, but for the most part, that should be the idea. And so the iterated integral is going to be something like 9 to 16. Then so this one's greater. This one should be at the top. This one's at the bottom, right? See if we get that part. Oh, so here it's kind of funny. Zero. Huh. We had like another way of doing it though, which is totally weird. Mm-hmm. Ah, there are a specific set of steps for this. So I have to find my upper y and my lower y. That's the first thing I have to do. And here I get two things, square root of x and negative square root of x. And then from there, what's the bounds of my x? It's from where to where? It's from 0 to 1 in this case. y 0 to 1. Wait, let me work back, see what I did. If I plug in, hmm, what in the world are my points here? Oh, so if I plug in, this is 1, then this is 4. 1 and 4. What? That's so confusing. Okay, let's not rely on that one, I guess. Okay. So here I have, yes, I have 9 to 16, x minus 12 to the square root of x, right? And this should give me that value, y dy dx. Then that's my iterated integral. Now I look at type 2. Type 2 is a double integral x dx dy, right? So this one, now I need something in terms of x. So how do I get that? Well, if I look at my bounded regions here, I get x is y squared. That's one thing we're given. Another thing is that x could be y plus 12. How do I know from here? X minus 12 is y, so y plus 12 is x. And so from there, well, now I put these in my outer integral for y is just the critical values here, the points of intersection, which are negative 3 to 4, right? And then this one is, so which one's bigger? Usually. So if I were to, how do I know which one to put in the upper and lower bound then? I guess I could try values from y, right? Mm, let me see. Yeah, because the y values should range from here. So obviously that's what I'm just gonna put. I'm gonna put like a negative 3 here. I get minus 3, I get 9. If I put here, I get 9. 4, I get the same thing, 16. But then how do I know which one's bigger? I plug in something in the middle, 0. This one's bigger, right? Usually. I can't put 100, obviously, because it's not within the range. And I guess it's also similar to this one. I put something in between 9 and 16 for this one. I put 9 here, I get negative 3, right? I put 9 here, I get 3. So this one's bigger, right? I put 16 here, I get 4. Put 16 here, I get 4. If I pick something in the middle, let's say 10, this one's going to be bigger. Or let's say if I put 12. This one becomes 0. This one is square root of 12, which is bigger than 0. So obviously this one's bigger. And so same here, we say that y plus 12 is bigger than y squared. And this is saying that for all points from negative 3 to 4. And here in this case, this is for all points 9 to 16, right? I think that's what it's saying. And so this is x dx dy. Now the question, which one is easier to solve? Dx dy is easier. Why? Because the limits of integration for x are simpler functions of y. So dx dy is easier. Honestly, I can't really tell, in my opinion. It just says that's easier. And then now if I start solving it, now I want to evaluate this thing. Well, I use that. So I use this thing. So I get y squared, y plus 12x dx, right? This will give me x squared over 2. I could just take out the 1/2. That's fine. Y plus 12, y squared. And then this one should give me y plus 12 squared over 2 minus y to the 4th over 2. And I could just factor out. So actually, I could have factored out the 1/2. So I get like 1/2 here. And then this one is some y plus 12 squared minus, and then this one is y to the 4th, right? And then I got something like, okay, y 1 over 2 is expand. Yeah, I want to expand this thing. This one gives me y plus 12, y plus 12. I get y squared plus, I think this was 24, 24y, 144. Then minus y to the 4th. So I get this. Right? And then from there, I can just evaluate it a little bit more. So I get minus y 4th over 2 plus y squared over 2 plus 12y plus 144 divided by 2. What is that? 72. Right? So that's that. And then I take that integral with respect to y. So from 3 to, what did I do? 3 to negative 4? Oh, negative 3 to 4. Negative 3 to 4 of this thing. Oh my goodness. Long, messy integral. So this is going to give me, okay. What can I do? What can I do? One, I'll straight up integrate. So I got negative, what's this? 1/2 of y 4th, right? So I get y 5th over 5. So negative y to the 5 over 10. And then this one is y squared over 2. And so this one becomes 1/2 times y squared, 1/2 y cubed third. So y cubed over 6. And then this one becomes 6y squared. And this one becomes 72y. Okay, last stuff here. There we go. And then from there, I just evaluate the whole thing. Whew, that's something. Oh God, why was the simplification so nice here? Um, why did I messed it up? Oh my, I did. I integrated with. Oh wait, no. Wait a minute. Am I doing it wrong? If dx dy was easier. Oh, what? Oh, it's still y. Oh my goodness. I said it here. It's gonna be y no matter what. Oh my gosh. So this is y. That's like my actual function. Y. This is my y. So okay. Okay. Nice. Very nice. Very nice. So I messed all of that up. I was like, wait, that is my function. I was like, I'm so confused. So here we integrate with respect to x. So we have xy here. Oops. Now I messed it up. I put a yx here. Y squared, y plus 12. Here I put that in my x. So I get y of this minus y squared, right? Please tell me I got that part. That was annoying. I was confused. Yeah, okay, that looks right. And I get y squared plus 12y minus y cubed. And then we integrate with respect to y. So here we have so that's why it seemed really, anyways. Now I integrate this thing, dy. And then there's yeah. So here I get straight up integrate. This one is 6y squared. This one is y fourth. Now I have to do all of that stuff. Okay, so if I do all of that stuff, I get 343 over 12. I have a solver. Okay, that's that. Nice. Okay, so we have more stuff to do here with solving double integrals with general regions. And so please stay tuned. I hope you guys enjoyed, and I'll see you all for that video.